going to focus particularly on how to make audio streaming, real-time audio streaming with very low resource IoT nodes. So the kind of nodes that runs on battery. And to give you some insight on the methodology that we took in determining whether the network infrastructure is capable of supporting real-time audio on such tiny devices. Okay. So first of all, you know that this is the main focus on SenZations, on Internet of Things. So there's a lot of connected objects that you can see here, and I'm not going to get into much detail of it, but you see that the goal is to make a lot of objects of our daily life connected in order to exploit some kind of geographical information and physical information. Okay, so I would like to emphasize that all this Internet of Things stuff are possible because we made, or they made, huge progress in wireless communication, and especially in making the wireless, the radio module smaller and smaller. So you can see the scale here, where you can have complete protocol stack with the radio, physical, map layer embedded in very small chips. That could be connected to any device. So it could make your fridge communicating, it could make your, of course, your smartphone, telephone, and so on. But this is one of the main reasons of such an advancement in Internet of Things research. Okay? And if we look at the radio system, we do have the whole, I would say, diversity of data rates and range. Okay, so you all know 2G, 3G, 4G, and so on. These are the networks deployed by the telco operators for mobile telephone. But you also have the well-known 802.11 wireless LAN, Bluetooth that we're using this way. This is probably not a Bluetooth one. This is more infrared. But my mouse is Bluetooth, and you have earplugs with Bluetooth with your mobile phone and so on. So you see this data rate of Bluetooth, you can go up to 1, 2, a little bit more than that, megabytes per second, when compared to wireless LAN. In Internet of Things, most of them, they use an 802.15.4, where you can see that the throughput is much lower, 250 kilobits per second. And the range could be up to 1 kilometer, so a little bit more sometime when you push the transmission power a little bit. I'm going to explain this a little bit later on. But roughly 1 kilometer is probably maximum that you can get with this kind of radio technology. So the reason most of Internet of Things, most of autonomous Internet of Things, I'm not talking about the Galileo board or the Beacon boards or other big board, Linux embedded board, where you need power to run them. Most of the autonomous Internet of Things, they choose this kind of technology because the power consumption is very low, at least 10 times lower than Bluetooth and more than 100 times lower than Wi-Fi. And this has a reason, because they deliberately choose to have very small power transmission, 1 milliwatt. You can be less than that, up to 100 milliwatt. Okay. In Europe, there is a regulation, and you cannot go beyond, I believe, 10 milliwatt or something like this. So it makes you have a range from 100 meters to about 1 kilometers. In line of sight, no buildings, no occlusion, and so on. Okay? And if you look at this curve, where you have Bluetooth, Wi-Fi, and 802.15.4, this curve shows that the signal-to-noise ratio and the bit error rate, you can achieve the same bit error rate with less in a smaller signal-to-noise. Okay? So that's the choice of this radio, to be able to be more robust, to interference more robust into signal-to-noise ratio, where you can have the same bit error rate, but with a smaller signal-to-noise ratio. Okay? So what is the price to pay? The price to pay is you only have this kind of throughput, and you have to stick with this. And I'm going to show you that even this throughput is quite small compared to what we used to have in Wi-Fi or Bluetooth. It is even smaller when you develop real application on top of this Internet of Things node. Okay? So far for some radio, I would say, background. And we have to say also that currently wireless sensors or embedded board are still the main IoT development platform. So we are using a number of them. And these sensor boards do have the processors. I'm showing here a Wasmot from Liberium. It's a Spain startup company. You see the processor here, the wireless radio devices. This is a DGXP module. And the sensing devices that you would plug on it. Okay? This could be optional, but in case of Internet of Things, you want to, of course, sense your environment. So you're going to put sensors here, gas sensors, event sensors, any kind of sensors that you want, any kind of sensors to detect any physical phenomena that you want to detect. And of course, there's plenty of development board. You have Arduino, you have iMod2, you have Crossbow Telos B, you have MicaSet here, you have Beagle Bones here. I think it's the previous version, not the black one. This is an embedded Linux. You have Raspberry, and of course we have the Galileo that you got here yesterday with the hands-on. Okay, so these last three represent probably what we call the high-end Internet of Things. Okay, because they really need power plug in order to be run. But anyway, they can be considered as an Internet of Things stuff. Now, there's a subtle difference. Maybe some of you ask this kind of question. What do we mean by IoT and what do we mean by wireless sensor networks? Okay? Because I just said that wireless sensor networks platform are usually used to develop IoT solutions. The subtle difference is when people talk about Internet of Things, they think about, of course, Internet technology. And Internet technology means how to integrate to the World Wide Web. It means that you're going to talk about IPv6, interoperability, interactions of all kinds, and usually semantic, ontology, web services, and so on. And 6LoWPAN, QoS, and so on. You are in the Internet of Things world. If you're talking about wireless sensor network, even if those two worlds are very close, we are more focused on how to organize them, how to make the programmability, how to schedule, how to have efficient MAC layer, how to route, how to handle congestion control, and so on. Roughly speaking, it's a little bit lower layer than Internet of Things, okay? More close to MAC layer, routing layer, and maybe physical layer for those who are interested in the radio communication. Okay, so that try to position or set the big picture of Internet of Things compared to wireless sensor networks. The fact is, when the Internet of Things concept appeared, a lot of companies started to see a real business model behind this. And one of the, I would say, most advanced business model is in the context of urban environment, smart cities, where actually it is very cost effective for the, let's say, people from the city to have, let's say, the trash bin connected. Why do we want to have trash bin connected? Well, you know, it costs a lot to, with a truck, to go to all these trash bins and try to empty them, just to discover that the trash bin is empty. Okay? And if the trash bin can say, oh, I'm almost full, please come over me in order to empty me, it's much more cost effective. Okay? So you can find a lot of applications in the context of smart cities, and I believe that you do have some kind of challenge to do here in working in teams. So in the context of urban environment, there is really a real business model behind this. Now, all these things could be summarized in what we call the control, optimize, and instrument control loop here, where you want to sense in order to perform data analysis, optimization, and control. So you have the up loop and then the down loop in order to interact with the different devices or infrastructures where you put your devices on. Now, let's go to the core of my talk. And we are more interested in multimedia information in our research group. So we started with image. We were doing for years image surveillance on wireless sensor networks. And then we move on in the context of area to sound. And these two senses are very important for humans. Okay? I'm not going to try to convince you. I believe that you're already convinced that vision and hearing are probably the two most important sense of human. So it's natural to try to use them also in so-called smart cities environment or smart environment in order to be able to have more information, more high-level information to your application. Okay? So we started with image, as I said to you, and there's a number of boards with embedded cameras. I do have a Pixie here. It's not very. It's quite brand new. It's an embedded camera that you could plug into an Arduino board. So probably you could put it on the Galileo board also. And you can train him to detect some patterns. Maybe some of you know about it. It's something like 70 euros. And if you put an apple in front of him and push a button, he will learn how to recognize an apple. And then when you take an apple again, he will say, oh, there's an apple here. And he could try to track up to 7 or 8 apples like this. Okay? So very, very nice devices and very useful when you want to build some kind of robot system or tracking system and so on. Okay? And actually, there are few studies on products for audio acoustic sensing. There are some, I'm not saying that they are not, but there's still some few studies regarding audio when compared to visual sensors. So in this project, the ERIT project, we want to exploit acoustic data in a number of advanced ways. And the number of application is always limited by your imagination. Here you could have sound mapping, traffic management, energy efficiency, audio surveillance, ambient assisted living, traffic accident, security, and I mean, a lot of applications could rely on audio and acoustic data. One advantage of audio when compared to visual sensors, you know what is the main advantage of it?
It's less expensive. Basically, the transactions and the type of message communication.
Yes, could be less expensive, but it's not the main. For me, it's not the main reason. For if you look at the sensing property, well, if you're talking about the visual sensors, you're limited by one direction. Mm-hmm. If you're not in line of sight, you're not going to see what's happened in your back. Okay. With sound, it's a little bit different. There's no line of sight. It's some kind of omnidirectional. So if you detect a gunshot, it could be behind, on my left, but I'll probably be able to detect it somehow. Okay? So this is a real advantage compared to visual. So this is
the disadvantage at the same time, right? Because you're also more susceptible to interference from anywhere.
Yes, but you know, I'm trusting the signal processing guy, and they say, oh, I can extract this kind of information from this. I reviewed a paper yesterday about they put some kind of microphone array on a UAV, you know, the quadrotors, and they want to detect screams of people in search and rescue applications. So what they did is, you know that the quadrotors are introducing a lot of noise, so it's difficult to capture the screaming sound. So what they did is they apply advanced signal processing to remove the sound of the quadrotors, and they have pre-recorded libraries, and they make some kind of best matching, and then they identify the noise pattern, and then they just remove it. They can do that, and I really trust them because I'm just not able to do this, but I'm sure that they can do this. So, in IRIT, we are using two complementary technologies. We are using some kind of advanced acoustic processing unit. So this advanced here is based on, if I don't remember, maybe it's Beagle Bone or something like this. Okay, Linux anyway.
Olimex.
Sorry?
It's the Olimex.
Yeah, Olimex, yeah, the red color.
Exactly.
Red color.
That's an Olympus, you know, they manufactured in my town.
Yeah, probably. Anyway, this is very powerful. This is a Linux-based computer. You could use this as the computer in your house. Okay, it needs power. But then the advantage is you can put very advanced signal processing to recognize sound. And then we also use the very tiny Internet of Things or wireless sensor networks. I mean, Internet of Things sometimes could be used for, let's say, marketing purposes. But a lot of these platforms are more so-called previously wireless sensor networks, wireless sensor nodes. So we also use these kind of things. And we want to combine these two. And I'm going to show you how we could combine them and why we should combine them. Okay? Because obviously, this is nice, but this is a little bit more costly. And you need power plant. And this one could run on battery. Okay? So these are very complementary. So in the IRIT project, this is a research experimental approach where we're using FIRE. FIRE is Future Internet Research Experiment. It's a European framework to define test bed for researchers for them to be able to test their solution. I just want to point out that it's very important when you're doing this kind of research to test on real environment where you have real deployment. There's no point for me to test in a room like this with, let's say, 50 sensors on the setting. For me, there's no point. It's much better to buy, let's say, 30 sensors, put it outside, strap them on the trees, on the buildings, and make your own test bed. And if you have access to one of the FIRE test beds, just go for it. Okay? So, the purpose here is to test these acoustic devices on large-scale FIRE networks and to define acoustic solution on this kind of large-scale test bed. Okay? So, we are using two platforms. The one that is represented by the Smart Santander. Some of them may be, you may be familiar with this project. I'm going to describe it a little bit in more detail. And the one with the UpNet test bed. UpNet is handled by Sebastian Ziegler, who was here, and he's probably in the IoT Lab meeting. And if you want more information about this, you could just refer to Sebastian to do that. And here in my talk, I'm going to describe the experiment that we did on the Smart Santander infrastructure. Okay? So Smart Santander is a very interesting test bed. Actually, it's more than 3 test beds, totalizing more than 20,000 IoT devices. Okay? Well, meanwhile, they change, let's say, wireless sensors into IoT somewhere or at some point, but it could be viewed as the 20,000 devices, autonomous devices. Okay? And we're going to focus on the one that is located in Santander. Santander is in the north of Spain, and they have more than, let's say, I believe it's more than 4,000 sensors deployed on lamplight, buildings, buses, and so on. You could see that. And if you go to the map of santander.eu, you can have the location of all of them. Okay, so this is a very interesting large test bed. And this is a kind of node that they're deploying. You can see the double antenna because it have the double network interfaces. And what's inside, you see this is a WASP mod. I'm going to give you, to show you, this is a Liberium WASP mod devices. Okay, and you see the two XB module, one for the control and one for the data. Okay, and these kind of devices are deployed across the city, and it's possible to download dynamically your program and to test it. Let's say if you want to test routing protocols, you want to test collection, data mining, any kind of algorithm that you want to test on a large scale, of course. And this is some detail about this, but I'm not going to spend much time on this. This is the Liberium WASP mod. You have the opportunity to see it, or maybe I can just pass on. Okay. So, the goal of this project in IRIT on Smart Santander is to use the APU and the small devices that have been deployed in the city. And what we want to do is, for example, emergency detection. If you detect an alarm, how do we detect an alarm? Well, the APU captures some sound and say, oh, it's a gunshot. Because I have the processing power to know that this is a gunshot. Okay? What happened? Well, I can rely on all the deployed sensors, the small one, deployed across the city, to try to detect where does the sound comes from. And if I know where does the sound comes from, if it's an ambulance here, I can try to synchronize my traffic light in order to say, oh, I'm going to give you a green light path for you to reach the destination fast. Okay? So this is one application, emergency detection. And you could have traffic monitoring also. I mean, the guy from Fraunhofer, one of the partners in the IRIT project, they are very strong in signal processing. And they told us, we are able to put a microphone somewhere with the APU and determine how many cars there are at a crossroad by measuring noise level and so on. So they can do that. And once you know the traffic density, you can try to encode this information in a data format. Okay? And one problem of this is, as I said, the number of APU is very limited because you have to deploy them manually on roof, on buildings, provide them enough electrical power to process the sound and so on. Okay? So you see that it's not really possible to deploy them on a large scale. Okay? So what we want to be able to do is to use the already deployed nodes, because Smart Santander do have them. They have more than 2,000 of these nodes already deployed. Why not using them in a complementary manner? So what I'm going to describe here is how we could use these small devices in order to be able to stream the audio data on real time from the source to some kind of control command center here. Let's assume that an APU detects a gunshot somewhere. The man here, he say, oh, there's something happened over there. He may have an application and say, I want to know what happened there. He click on the sensors on this area and he gets a sample of the sound, what happened. If they're hearing people screaming or shouting, or they can get, let's say, 10 seconds, 20 seconds of real-time audio in order to know exactly what's going on in this area. Yes.
But wouldn't you rather try, because of the limitations that you have in terms of bandwidth, you rather try to stream just events rather than raw sound?
Yes, we are also doing this. This is called some kind of acoustic metadata. Not getting the audio stream, but let's say more the information that it's a clock crash or it's a gunshot or yes, of course. But still, you don't know what's going on really. It may be much more interesting to, in addition to this data, to know, what people are saying, are they shouting, are they screaming, and what are they saying? Okay. Of course, there's a lot of privacy problem, and one part of the project is dealing about privacy. But if you remove the privacy aspect, then there's a lot of nice applications when you're able to get the audio stream in order for a human operator to see, what's going on there. So this is the main motivation. I would like to review, in case some of you are a bit short about digital audio. It's going to be very quick, but it's good to approximately know the basics, just to understand what I'm going to talk later on. When you start with analog signal, you're going to sample it, okay, at a given frequency. Then you're going to try to quantize the signal between 0 and whatever you want, how many bits you want, 10 bits, 8 bits, and so on. And then when you have quantized, you have a single digital signal, and you are able to, okay? And I'm not an expert of this, but I know that there's a Shannon's law saying that if you have a signal of frequency, let's say 4 kilohertz, then you have to sample and double the frequency, okay, at 8 kilohertz. Okay? So, narrowband audio use 8 kilohertz or below 8 kilohertz sampling. If you use 8 kilohertz sampling, you have one sample every 125 microseconds. This is the basis of most of the telephone systems. Sampler could be coded on 8 bits. So if you have your conversion on 10 bits, you have to reduce it to 8 bits somehow. So you have a raw throughput of 64 kilobits per second. This is what we call the so-called pulse code modulation using most wired telephone systems. With 4 kilohertz sampling, you can reduce the raw throughput to 32 kilobits per second. Okay? So 64, when you compare it with the radio of 802.24, you say, well, there should be no problem. I have, on one hand, 250 kilobits per second, and I need 64 kilobits per second. No problem. So, the principle of audio streaming is when you got the different signals and you've got a number of samples, you divide them into, let's say, time interval, let's say 20 milliseconds, and you try to send them. And usually at the receiver, I mean, this is basic things on streaming, when you're clicking on YouTube or anything, it works like this. You have your inter-arrival time. Since you may have jitter between packets, you're using a playout buffer here, and you try to play out the audio regularly using your playout buffer. Okay? So this is the principle of streaming, and this is very easy to perform on a computer like this because you have all the leading software to make playing, buffering, and so on. Now, do you know the difference between microprocessors? Because we all speak about, oh, this has a microprocessors, but this has a microcontroller. What's the difference between a microcontroller and a microprocessor?
Controls things.
You know, I can have a JPEG compression algorithm running on this microcontroller. So it's not about. Oh, I can have a real operating system.
Normally they don't have the point, float point support. They only have one vector to keep everything.
Yes, but on some advanced microcontroller, you do have floating point also. So it's not the difference. you'll be partly right when you say controlling, but it's not like that. The real difference is the microcontroller is a standalone piece of silicon. It has all the memory, all the processing, everything. It can work standalone. If you're using a microprocessor, you need an external memory, RAM, SD-RAM, and so on. Okay? And also, one features of microcontroller is they do have dedicated port to interact with the physical environment. Meaning that they have pins to natively perform analog to digital conversion, or they have pins to control the power input, power output, and so on. Okay? This is the main difference between microcontroller versus microprocessor. Okay? So let's assume, for example, that you have an input voltage between 0 and 5.3. The analog digital converter, one of these pins, this one has 7 or 8 of them. One of these pins can just read the value. If it's on 10 bits, then if you read 0, it means that you have 0 volt. If you read 0.4, it means you have 3.3 volt. If you plug, let's say, a luminosity sensor, and if you read something here, you can derive the luminosity density. And if you plug, let's say, a microphone, and if you read something here, you can deduce the sound pressure level between 0 and the resolution of the analog digital converter. Okay? So, this is what we are doing. So, the small board that you have, I don't know where it is right now. Okay, over there. We plug an electret microphone here, very small, with amplifier with, let's say, 2 or 3 transistors. We plug it on one of the analog to digital converters here, audio on analog 2, ground on the ground here, and VCC, the power, on one of the digital port. And you know that in this kind of platform you can output a digital port, say, okay, I want to make it on. Then you have 3.3 volt on this pin, and then it will power on your microphone, and then it's working. And then you will sample what happened on analog 2. And this is what we're doing here. This is to initialize the timer. I want to sample every 125 microseconds. This is Arduino sketch. So you could probably, you're now used to it, you could probably do that on the Galileo, I believe, or on a regular one. So we're using a library timer, and we initialize them to timing sampling. Timing sampling is 125 microseconds. Once every 125 microseconds. And then I have a periodic behavior. Could you give me back the audio board? Where is it? Okay, thank you. So what I did is I put a LED here, LED, showing when it is capturing. And I program it to say, if I switch it on, every 15 seconds it's going on, off, again. When it's on, the LED is going to be on. And I can speak to the microphone. And if I have the right receiver on my laptop, I will get the audio stream. See? So it's capturing, hello, 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 but I didn't plug the gateway over there. But if I have time or offline, I can show you how it works. Okay? So here we just have the control logic to say, am I sleeping for 15 seconds? If yes, then I have to wake up. Okay? And if I'm waking up, what I'm going to do is, I'm continuously reading analog 2 to get the sound pressure. Okay? That's it. And then I'm realizing the analog to digital conversion, and then I can use any way of transmitting it. Okay? So I'm going to describe this a little bit later on. Now, if we go back to this slide, the question is, how or to what extent can you swap real-time or near real-time audio traffic on these very small devices. Okay? So, if you're talking about multi-hub audio streaming, you have many overheads. One overhead is on the sending side. Am I capable of sending that fast? That's the question. If I'm not capable of sending that fast, let's say one packet every 20 milliseconds, then I'm not going to be able to send my audio signal. But it's not at all. If I want to be able to relay, am I capable of relaying the data that fast? And I will show you that things are not easy on these devices. If you can send it fast, maybe you're not going to be able to relay fast enough. And we have to find tricks or mechanisms to make it work. Okay? So I'm going to go back to this later. So before we did all this work on audio on smartphone tender, we got some kind of preliminary studies in order to benchmark and to qualify the smartphone tender or any testbed that you want to run your audio traffic on. We have to know what are the minimum latencies and maximum throughput for sending, for receiving, for relaying. If you are not capable of sustaining this constraint of audio, just forget it. Okay? So, fortunately, I'm showing you that we were successful in doing this in a number of ways. So, if we look at this, let's say, mass market sensors, Arduino, Libelium, most of them are based on UART connection. UART is a serial line, okay, between the radio module and the microcontroller. The problem is it is very limited in terms of throughput because UART connection could be run at, let's say, 115,000 baud, but these boards usually use 38,400 baud, so bit per second in this case. So it's very limited. You do have also academic sensors. IMO2, very powerful one, but a little bit old. Mikase, Tilus B, Galileo, and so on. These use probably much higher or much more elaborated buses to connect the radio module to the microcontroller with an SPI bus. So you have the speed in the order of several hundreds of kilobits per second available. Okay? So usually on this kind of sensors, you do have more performances. Unfortunately, in Smart and Tender, there are more than 2,000 devices like this, and they run at this bit rate between the radio module and the microcontroller. So when you want to transmit your audio signal, you are limited by this speed. Of course, you can try to improve the speed, to increase it, but we did this, and I'm telling you, it's possible, but you have to take care about the frequency of the microcontroller, the frequency of the radio module, and you have to find the common integer divider in order to make it run. If you're using standard baud rate, it's not going to work. Okay? So we tested it and we ended up with 125,000 baud. It's not a standard baud rate.
But the XP cannot be connected to the SPI port as well?
No, not the XP. The XP runs on only serial.
Only serial?
Yeah, only serial. If you take a CC2420, you could have the XPI bus. Or if you take another one from, let's say, Maxwell, or you can have other connectivity like I2C or SPI. But the XP is very flexible, very versatile, but only serial now. Okay? So this is one of the limitations. Now, regarding the sending performance, let's see what we got. We want to know what is the maximum throughput you can get on this kind of board. And we have a traffic generator. We developed a traffic generator in order to measure the time between the send function and then between two consecutive sending, two different meters. The time spent in the send function and the time between two packet sending. And we are trying to send packet back to back as fast as possible. Okay? And this is what we got. I want to tell you that these are the figures with all the optimization possible that we made on these devices.
You are also accounting for the acknowledgement time, or is
No.
it's not acknowledged?
No acknowledgement. We want to have the best performance. The acknowledgement is not going to add significant overhead because it's done on the Mac layer. So usually it's done in the hardware. Okay? And it's in terms of hundreds of microseconds. So it doesn't really matter.
But in encrypted communication, you also have to decrypt to know.
Yeah, but once again, we are trying to have the best case. So no encryption and so on. If you have encryption, obviously this is going to be higher. But we want to have the best cases. What could we have without any additional overhead? What could we have is if we optimize the communication speed between the XB module to the microcontroller to 125 baud, and we optimize also the library, the API, the programming library, we were able to obtain something like 16 milliseconds between two consecutive sends on this kind of devices for a 100 byte radio packet. Okay? The problem is I need to be able to send in raw audio. If I'm using 8 kHz sampling, I need to be able to send 100 bytes every 12.5 milliseconds. Not possible here. I mean, I'm above this. I need to have 12.5 and I have, at the base case, 16 milliseconds. But if I'm using, let's say, 4 kHz sampling, I only need 25 milliseconds. So I would say, well, it's possible, 16, 25. If I'm downsampling to 4 kHz, it's possible. Well, no. Why? These figures are true, but the problem is, if you're sampling, you cannot transmit at the same time. Because sampling takes all your microcontroller processing resources. No way to sample at 4 kHz and to transmit at the same time. So even if you're only doing sending, you can achieve 16 milliseconds. If you're doing sampling at the same time, no way. Okay? So one problem with the board that I'm showing here is you cannot do it right now. So one solution is, okay, before saying the solution, I just want to point out the maximum application level throughput here. You can see that the maximum realistic throughput is less than 50 kilobits per second. And this is the maximum performance that we got. I think it's going to be very hard to be more performant than that. Because we optimized a lot of things here and we only got 50 kilobits per second. If you compare this to 250 kilobits per second, you see that there's a very huge gap, very huge difference between the radio throughput and what you can get at the application level.
What is the main reason for it?
Cost of API, all the API processing, building the packets, transmitting it through the route line to the radio module, memory operation, copying data, and so on. All this overhead makes that at the application level, when you're dealing with this kind of platform, you have to know that the throughput you got at the end level, at the application layer, is no way close to the radio throughput.
Okay, so in this case, basically the limitation was the microcontroller on the node, on the libelling node, rather than, so if I would stick the let's say XB module onto, let's say, a bigger node, let's say like a Raspberry Pi or whatever, then it would be able to have higher throughput, right?
Yes, but not that much, because you will be limited by the communication between your radio module and the microcontroller. So maybe the processing is a little bit faster, but you still have the memory operation that they copy. So that depends on the size of the bus, and it's going to cost you.
So is it now the UART concept is limiting, or is it the MCU processing that's limiting?
But at the end, you are also going to have the transceiver limitation because you can only store that in the FIFO queues as fast as the SPA communication allows you, and you have to manage the storing sequences and all the communication sequences to send the data. You are also limited by the time operation of the transceiver besides the...
Yeah, I was just trying to understand, like, in this case, what was actually limited.
There are many limitations. Certainly the microcontroller has its I would say, limitation, but we did it on the Arduino. Arduino is a 16 megahertz instead of 8 megahertz microcontroller, and we were able to have a little bit higher throughput, but not that much. It's not going to double. Okay, now, if we know this limitation, one way of enhancing it is to say, if I cannot make the sampling and the transmission at the same time, I have to dedicate it one resource to sampling and one resource to transmission. What can we do with the XP? The XP is versatile, very flexible, because one of the reasons is because it already has an embedded microcontroller on it. Okay? On this little piece of Sicilium, you do have a microcontroller. I don't remember which one. It varies with the version of the XP module, but you do have a microcontroller. If you plug it, you don't have to program it. You have the microcontroller taking care of all the stuff. Okay? So what happened is we configure the XP into what we call transparent mode, where the microcontroller takes care of all the framing. You just have to send it the data, and it will fill in the FIFO buffer. When it reaches 100, just send it out, make all the framing and so on. And this is how we made it possible. Meaning that if you send hello, you just have to send hello to the XB module. Like I'm sending hello here. The XB module is making all the framing according to 802.15.4 standard. And all the microcontroller on the XB module will construct the frame, put the hello here, and send it to the other side. The limitation of this is, okay, I'm sampling the value, analog 2. I'm writing the value that I have computed. I convert it in 8-bit, and then I'm sending it to the radio module just by writing the value on the serial line. It's very simple, and it's working. And if you do it, you can have a Python script reading the serial line and feeding it to the play in order to have buffering, raw data, this is sampling rate, and it works. I can show you how it works, but it works. 8 kilohertz sampling, transmission using the XB microcontroller to perform all the sampling, all the transmission of the time.
One question, did you also change, for example, you are not doing any backup, or are you doing fixed backup to access the media? Because the XB, I believe, goes on CSA-MA.
We're not doing backup. The DE exponent is set to 0. By default, it's free, but we're not using it. We don't have backup. The backup, there's no backup.
So you are accessing the media as it is, and you don't care if the media is busy, but injecting packets.
Yeah, for the moment, we only have one source. Yeah.
So that's interesting. So to understand, right, in the previous case, you did all this framing on the microcontroller.
Yeah.
Okay.
We constructed frame. This is a regular API. Why do we have the, I would say, what is the advantage of constructing the frame? One advantage is you can say to whom I am going to send the frame. If I'm not constructing the frame and I let the XB module do it, it's only one hop, because the destination is hard-coded on the XB.
But you can control that. No?
You can control it, but it's going to be very costly. If for every packet you say, oh, I will change the destination, I have to send 80 commands to the XP module to change your register.
But actually, usually you don't kind of change on a packet per packet basis the destination, which I mean in this kind of application.
You're right. You're right. But the problem is if you have multi-hop, you're sending one hop, but there's a one. You have to know where it's going to send. See? So you have to configure previously. So
but you know,
it's trackable.
But you do is like kind of source routing, what you just say, like where you have hop.
You can do this. You can do this. It's trackable. It's trackable, but it's not very flexible. So if you really want to do this, I'm not saying that it's not possible. You can construct the static part, configuring all your XP, saying that this one has to send to this one has to send to this one has to send to this one, and then configure it as a transparent mode. You can do, let's say, 1, 2, 3 hops like this. It's possible. But if you want to change the destination, it's going to be very costly, and you cannot do it on the fly. Okay. So now, this second solution we took is we developed an audio board. We said, okay, raw audio is not very tractable. So we developed an audio board, okay, and which has its own microcontroller on it. That could be programmed very easily. This is a DSPIC, very powerful microcontroller. And they do have the library to perform speech encoding audio. So you're going to real-time encode the audio to provide an 8 kilobit per second audio stream. Okay? You just plug this audio board on, let's say this has been developed for the Telos B with the 51 pin, but, I mean I can, okay? But it's also possible, and I'm going to pass it also, to have the same audio board connected to a WASMOD, because all the communication is performed with serial line. Okay? So it's very possible to do this, and it's a very powerful solution. So the principle is the audio board is going to capture raw audio and real-time encode it. You're going to end up with 20 bytes every 20 milliseconds. And, yeah, and it's going to send this data through a serial line to the host microcontroller. And then once you've got this data on the microcontroller, you can do whatever you want with it. Okay?
So you're offloading the processing basically.
We are offloading the sampling and encoding, real-time encoding. Okay? And you can really decrease the throughput required.
But what kind of encoding did you do?
Speaks.
But what you did, you say just, okay, you kind of just sampled down currently from 10 to 8 bits, right? That was the only kind of encoding that you did before.
Okay, I'm going to explain it.
Sorry.
I'm going to explain. Okay, so this is the audio board on Telos B. It's also possible to plug in on a WASMOD using, serial line. And I believe that it's possible to plug it on the Galileo. Okay, so if some of you want to try it, no problem. I will go for it. I'll be happy to see whether it works or not. I do have all the program on the WASMOD, so you can take them and inspire yourself from them in order to make it work on the Intel's Galileo device. Sure. Plug it again. Now, a little bit more on the SPICS codec. SPICS is very, I would say, very powerful. You take 168-bit sample, meaning that you take 20 milliseconds of audio. You encode it, and you have a resulting of 20 bytes of encoded audio. 20 bytes every 20 milliseconds. Much more tractable than raw audio. Okay? And we do have framing bytes. So in total, we have something like 24 bytes every 20 milliseconds. This is the constraint. Summary. If you're doing raw, 4 kilohertz, 8 kilohertz, if you're using SPICS, no aggregation, 20 bytes every 20 milliseconds. You can perform audio aggregation, saying that you sample 2 frames and you send it in one radio frame, so you have a time window of 40 milliseconds and so on, up to A4. A4 you have 95, 96 bytes. It's almost maximum because the maximum is 100 bytes. Okay, so you can do A4 aggregation. Okay, let's look back at the performance that we had previously with this. Now it's possible to send real-time audio because the sending time is lower. 24 bytes every 20 milliseconds. It's possible here. I have 8 milliseconds. If I'm using A2 aggregation, I have 50 bytes. Still possible because 50 bytes require something like 40 milliseconds. It's possible here. If I'm using A3 aggregation, 3 audio frames is 75 bytes. It requires 60 milliseconds. Possible here, and so on. Okay, so with this solution, we are able to stream in real time using the sending mode here. Now, if you buy one of these WASMOD, if you buy it from Libelium, and you want to try to use it, these are the raw performances that we got off the shelf without any optimization. 46 milliseconds. 46 milliseconds to send 100 bytes. We managed to make it from 46 milliseconds to 16 milliseconds. Okay? So we saved 30 milliseconds. It's huge. We optimize the API and we increase the communication speed. And we were able to have this level of performances. So if you want to fully exploit this kind of WASMOD, a lot of people say, oh, WASMOD, they are bullshit because we cannot, we cannot have fast communication and so on. Yes, it's true. If you buy them off the shelf, it's true. If you try to tune them, it's quite efficient. 16 milliseconds. It's not. I mean, it's not a Ferrari, but it's quite. For this kind of platform, it's quite fast. So if you have the off-the-shelf platform, you can hardly get more than, maybe you cannot read it, but it's 18,000 kilobits per second. Only 18,000 kilobits per second. Only. 18 kilobits per second. Only. We managed to have almost 50 kilobits per second. Okay? Now, if you are using the Telos B is a little bit different, it's a little bit faster, but look, it's not that fast. Even though the radio module is connected through an SPI bus, it's not that fast, because we managed to have less than that on the WASMOD by optimizing all the API and so on. This is a TinyOS performance using TKN154 protocol stack, which is quite fast, and we got 25 milliseconds between 2 consecutive sends. And this is probably the maximum, the minimum amount of latency we got on this kind of device. I'll be happy, because I know that you are one of the developers of TinyOS, I'll be happy to see whether there's a way to optimize this further. But really, this is the minimum time between 2 packet sends that we were able to
have taken as low as 12 milliseconds, but using another MCU clock at 16 megahertz.
Yeah, so it's not the regular Telos.
No, Telos B, in fact, the default version is clocked at 1 megahertz, but you can clock it at 4 megahertz. So maybe if you increase the frequency, you can get more.
A little bit more, probably.
Yeah.
So it will be interesting to figure it out. But anyway, if you buy this off the shelf, once again, and you program it in order to be able to send faster, very fast, you can get something like 25 milliseconds. Okay? So, what does it mean? If I'm sending one audio frame, I need 20 milliseconds. I say, wow, I have 19 milliseconds, 19.7 milliseconds. So it should be possible. Well, 19.7, it's the mean. But sometimes you are below, sometimes you are above the mean. Okay, so if you look at all these samples here, sometimes you are well above 20 milliseconds, and that makes problem. So clearly here, it's not really tractable to use one audio frame in one radio packet. It's much better to perform aggregation and to send two audio frames into one radio frame in order to have a time window of 40 milliseconds. And 40 milliseconds, it's okay. I only need 21 milliseconds to send the 50 byte packet. I have plenty of time for my other processing stuff. Okay? So this is very tractable.
Just to make us give an idea of, okay, if I use, for instance, A4 encoding, what you say, I introduce, so what's the effect of it in terms of my audio
stream? You have a little bit latency because, you have to sample and keep four audio. 4 audio is 80 milliseconds, but really it's not that noticeable because 80 milliseconds is too fast. Yeah, if it's going to be like 200 milliseconds, then you will notice it. With satellite telephony system, you do have this kind of delays, so you see that there's a problem.
But I guess the delay affects you only if you actually have two-way communication, right?
Yeah.
If it's just one way, if it happens like half a second earlier or later, you feel really,
Yes, yeah.
One question. How are you handling self-interface, for example, in a 1 or 2 or 3 hop network, isolated network, this may work well. You have some collateral place networks aside, or you have a high density of nodes. You are interfering with each other.
Yes, of course. I can answer very quickly. For the moment, we didn't study all these interferences because we said, I want to be able to run it in the best case. One source going to the sink. Of course, if you have two audio sources in the same neighborhood, you have to perform some kind of which source I'm going to select. This is another problem. This is, let's say, a scheduling problem or a selection problem. It could be based on what is the one with the highest battery level, what is the one closest to the accident, I'm going to select it. Okay? But so, I mean that this is a higher level problem. And if you're talking about interference, let's say intrapath interference, actually we didn't notice much interference on all the relay nodes. One reason is if you're using audio aggregation, you have one packet every 40 milliseconds. 40 milliseconds. You need about 4 milliseconds at the radio level to send it. So the contention time on the medium is 4 milliseconds. So when the first one is sending to the first relay node, it already finished the transmission. It hasn't begun the other transmission, and the relay node already transmitted to the other one. So the intra-path interference is not that much. We noticed it that for audio, and audio is a very constrained traffic, we didn't notice it much interference because of the time window that is quite long. So now that I convinced you that it's possible to send that fast, the problem is, am I able to receive that fast? Okay, because what does it mean to relay? Relay means I receive it, copy it in memory, and transmit it again. Look at this graph. I need 50 milliseconds on the WAS mode to read 100 byte packet. 50 milliseconds to read this.
Quicker, longer than you said, yeah.
50 milliseconds. Why? Memory copy, serial line reading, pulling, I need that amount of time. What does it mean? It means that the sending throughput may be up to 50 kilobits per second, but the receiving throughput is only, let's say, 20 kilobits per second. So when you want to relay, it's much slower, okay? And if you're taking one of those advanced SPI buses, the read time is much lower. like this. On the advantixis, you have something like 8 milliseconds. Is it? Yes, 8 milliseconds to read 100. So much more efficient on this kind of devices. So if you want to build a relay node, take this one. It's even better with a Mica Z. Mica Z has almost 10 years old. But they are really efficient. I keep a bunch of them in my lab because if I want to build a relay node, I'm using this one. Because I'm capable of relaying in less than 16 milliseconds. Very fast, okay? Very, very fast.
And what's the reason for them being fast?
Because the architecture is much simpler, because I don't know exactly why, there's a good matching between the microcontroller frequency and also, but it's an empirical study, and we say, Mica Z, if you do have them in your drawer somewhere and you forgot them, just use them back, because they are very good for building relay nodes in a test bed. Now, if you look at the relay performance, look at this. We need on the WASP mode, and once again, these are the nodes that are deployed in SenZations, so no way to change them. We have to stick with them. You need about 60 milliseconds to relay a packet, a 100 byte packet. It means that if you're relaying a 25 byte packet, one audio frame to one radio packet, you have something that more than 20 milliseconds. No way to relay it, because you're going to fill in the receive buffer, you're going to scratch your system completely. Okay? No way to, because you don't have enough memory to store the packets. Really, it's completely impossible here. It may be possible to relay 2 audio packets, aggregation, aggregated with 50 bytes here, because you need 40 milliseconds, and you need here 37. So it's a little bit tractable. But I would not advise you to do this, because sometimes you may have 37, but sometimes you may have 42. In 42, you're going to build up your buffer, and it's going to scratch randomly, and you don't know why, because you don't have enough memory to store the packet. So I would advise, and this is what we did, if we have to relay it on the WASP mode, we are using A3 aggregation, because we can relay it in less than 50 milliseconds, and we have a time window of 60 milliseconds. Okay, so this is tractable. Now, if we're looking at SenZations limitation, because it is realistic in SenZations to fully optimize the modes on which you plug the audio board, because you're not going to deploy that many audio boards. Okay? But it's completely unrealistic to reconfigure all these nodes of SenZations for relaying to optimize the API and so on. It's just impossible.
And didn't you say you can actually reprogram the module?
Yes, but we talked to them, and it's very difficult for them to allow us to change all the lower levels for this. They can do this on, let's say, 20 sensors for us.
Okay.
But they cannot make the whole network operation under this new configuration, because they have a lot of, background traffic, lots of applications, and they have, when you change the communication speed on all the API, you have to flash all the nodes with a new API, and the new API is not compatible with the old one, and so on.
Yeah, okay.
So it's not tractable.
Yeah.
So it's completely unrealistic. So we have to do with it. So on SenZations, the problem is we have this amount of latency to relay a 100 byte packet. More than 100 milliseconds to relay a 100 byte packet. Okay? So if I'm doing A1 aggregation, it's not possible. Not possible to do A2 aggregation. Not possible to do A3 aggregation. Not possible to do A4 aggregation. So what can I do? The only solution is I have to discard audio frame as a source. I'm going to take one audio frame and say, I'm not sending it. I'm going to aggregate 6 audio frames by discarding 2 of them, so I only have 4 audio frames, and I put this in a radio packet. That will provide me a time window of 120 milliseconds tractable here. But I do have 33% loss at the source. So that degrades heavily the audio quality, but it's possible. Okay? Okay, so now if I'm using this kind of hardware, I can manage to have this relaying. So I can have A2 aggregation and be able to relay it on real time with the TLOSB relaying. If I'm using MicaZ, it's even better. Okay? Now, this is summary on performances. And what I want to highlight is if you work on wire sensor networks and you work on applications on wire sensor networks or IET nodes and so on, please take the real figures. Don't say that you have 250 kilobits per second available for your application. It is not true. At the best case, you have something like 70 kilobits per second, and you have to do with it. You have to design your control mechanism, you have to design your scaling mechanism by knowing that you have 60 kilobits per second and not 250 kilobits per second as your application. So also if you're doing simulation model, please do not assume that you have the 250 kilobits per second as your application model. This is really important if you want to have realistic reasons. And we published a paper recently by studying all the performances for iMod2, MicaZ, Arduino, WASMod, and TLOSB, all these five, comparing each one to each other, and indicating all the best case time for sending, relaying, reading. If you want to have real measures, real figures to plug into simulation models, use these kind of figures instead of saying that you have 250 kilobits. Okay? So this is a small message. Now, I do have a couple of minutes to go, and I just want to show you that once you make this study, it's also interesting to see what is the audio quality that I can get. Okay? So what we're doing is we introduce packet losses. Random packet losses, independent packet losses. We apply this and we compute it something like a mean opinion score, MOS value, on the audio that you are receiving. And the results is, if you're using raw audio, you know, this one, raw audio 8 kHz sampling, you can support up to 50% packet loss. It's still understandable. If you're using SPICs, the encoded audio, you can support up to 35% packet loss, and you still can recognize the voice. Okay? So, I mean, 35 packet loss is still tractable. So, what we did is we went to Santander last February. We selected a number of locations. Line of sight location, non-line of sight location, open space or urban area and so on. I'm going to show you the results of one-hop audio in line of sight. We went to the marina. The distance between the audio board and the receiver here is approximately 300 meters or 200 meters, so much more than the 100 meters because the modes in Santander has more transmission power than the regular one. And we're using Wireshark. We have a sniffer based on the TLOSB like this. We're using Wireshark, and we capture all the messages that are sent here. We can compute the relay latency with using Wireshark here, and this is what we got: one-hop audio, almost no packet loss. This is A6 aggregation, so you have 120 milliseconds between two radio packets. Okay, so you see that you are quite stable here. Here you have the 15 second on for 15 seconds, off for 15 seconds.
Is it A620? Isn't it too big in terms of payload for the radio?
No, A6, but I explained previously. A6 means you capture 6 frames, you discard 2, and you only keep 4. Because otherwise it's not trackable because the time window is too small. So we have almost no packet losses. If we're using the audio board, we have something like 8% packet loss. What is the reason? You know? Why do you have more packet loss with this audio board than the one with the fast-mode audio? One very simple reason is the XP in Santander, they have 10 milliwatt transmission power. And the radio module on this is limited to 1 milliwatt. So the power transmission is much smaller on these devices than on this one. Okay? So this is why on such a distance you do have 8% packet loss. If you have only, let's say, 80 meters, you will not have packet loss. Okay? But 8% packet loss is trackable. I mean, I showed that you can understand up to 35% packet loss. So 8% is almost nothing. Now, very more challenging. Non-line of sight. You have a wall here, we place the source here, and we have to transmit up to there, non-line of sight. You don't see the source, you don't see the destination, you have buildings in between. What happened with the WASP mode, we have more than 62% packet loss. So you can see that in smart cities, when you have buildings and so on, it's very difficult to have line of sight transmission. It's very difficult to have transmission quality. If you want to be able to increase the reliability, you have to make relay. And this is the next experiment. We put a relay node here, okay? Here, one relay node. So from the source to the destination, we don't have line of sight, but thanks to the relay, we were able to have very few packet losses. Yeah, okay? So I would just want to point out that this is only possible because we use encoded audio. Once again, it's very difficult to do multi-hop relay with raw audio because it's too demanding in terms of resources. So we use encoded audio, and we test it up to 3 nodes, 3 hops, and it's working fine. I speak in the microphone here, 3 hops later, I can get almost in real time the audio streaming playing out in my computer. Okay? Regarding energy consumption, it costs me, when I'm here with the audio board, something like 68 milliwatt. And when I'm sampling and encoding, it's going to cost me 330 milliwatt. Okay? So it means that if I'm running on this kind of battery, the 2AA battery like this, 2AA battery, okay, I can transmit and capture for 15 hours. That's okay, 15 hours. Knowing that most of these scenarios are done in what we call a smart city, most of the sensors can be recharged at night because they are power plugged on the lamplight and so on. So they are not fully autonomous in the context of smart cities. Okay? There's always a way to put solar panels or power from the street light, or power from any kind of, in order to recharge them from time to time. So doing so make this scenario very practical. If I need, let's say, 1 minute of audio streaming, there's no problem for this device to do it. Because I have up to 15 hours with this 2AA battery. Okay? If I want to relay it, it's a little bit different. If I want to relay it, I need more energy, and I can only relay for 1 hour and 20 with the same node. So this is why, in this case, you have to maybe use multipath routing or organizing your network so that you're not using the same relay node if you know that you are using the relay node for something else. Because relaying audio traffic is very costly in terms of energy on this kind of devices. Okay? Okay. So, conclusion. I just want to conclude here. What we did is we benchmark the testbed in order to know exactly what are the capability of the testbed. This is very important. And we do have a whole benchmark procedures. I just want to give this message to those of you who have testbed. We have a set of tools, all the software described, all the package described to benchmark a testbed, 802.15.4 testbed, to determine whether your node is capable of supporting real-time audio or not, relying on the constraint of the real-time audio, the encoded audio. Okay? So these benchmarking procedures was very important for our project, and I believe that it's going to be very important to determine for all the testbeds the real performance level that you can get. And then we shown the main performance issues, and for those of you who are interested in these performance issues, well, you can talk to me later on, or I can give you references to papers working that describing performance studies of this. And we apply synthetic workload in order to qualify the testbed and to propose mechanisms to have near real-time audio. Okay? And that concludes my talk. The slides will be available on the website, so I put an additional reference here. You can have a look at them and download them if you want. Also, the developer audio board, if you want to have one of these, they can sell it, they sell it to us because it's a dedicated requirement. We ask INRIA in France to develop the audio board for us. We are not electronic specialists, so we ask them to develop it. If you want, if you're interested in, it costs about 200 euros, the audio board. You can contact us to have one of them, or some of them. And it's very versatile because we were able to connect it on the USB. It's possible to connect it on the Watt mode. I'm sure it's possible to connect it in any sensors with a serial line. We have basic communication. Okay? And it's completely standalone. Completely standalone. When it's power on, it provides 20 bytes every 20 milliseconds to the graph base, and you just have to read the data and do whatever you want with it. Okay? And well, thank you for your attention, and if you have any questions, I'll be happy to answer them. And also, maybe I can try to find some time to make some demo, or maybe if we have 5 minutes, I can just make a small demo of encoded audio just to show you something. Okay, thank you very much.